Hi, and today what we're going to do is we're going to talk about something that is pretty frequent to me as a chemist, and that's the idea of dissolving substances. So what I've got over here is a substance that I'm going to dissolve in this water. I'm just going to take a little bit and show you what this is about. So I'm going to, it's a blue substance, and I'll give it a stir. There's the camera. I want you to try and think, what is actually happening when I do this? I use a glass rod, it's a beaker. And some of you may recognize this substance as being copper sulfate, copper 2 sulfate I should say. And as you can tell, when I stir this, the copper 2 sulfate solids that were there before are now starting to, I'd hesitate to say vanish, but they're no longer seen. There's certainly less of them. I just pause it there, pause my stirring. So I can still see a few, and give it a little more stir, and very, very few, if any, it's gone. Okay, so it's a little bit. So it's definitely something's happening. Okay, the first question I'd like to ask people to think about is this a physical change, or is it a chemical change? Now, physical changes and chemical changes you may have met at a much earlier stage. I'm thinking maybe year 7s. So is this a physical change or is it a chemical change? Now, a physical change would be something that is easily reversible. So when I talk to my students, I have to get them to think, how can you actually reverse this? Now, this would actually be relatively easy to reverse if I was able to separate out the water. So if I just left it on the side on a warm day, all of the water molecules would actually evaporate away. And this I'm actually talking about water molecules. And I would then end up with my original copper sulfate. If I was lucky, I might actually end up with a sample that forms a crystal. Here's one that I did at a much earlier stage. I used a lot more copper 2 sulfate to dissolve, and I left it to crystallize. It's a beautiful crystal, fantastic sample. So not only is solubility quite important as a chemist, but it's also something that we can also appreciate in terms of the beauty. So what is actually happening here? Well, first of all, I think people just generally have an issue with this topic because there's so much vocabulary that you have to learn. Now let's just be very, very clear on this one. Now, the solid that you can use to dissolve is called a solute. Okay, so that is a solute. It's the substance that dissolves. The original water that I had, and water is a great example of this, but there are some substances that cannot dissolve in water. There are other solvents that you can use, and I just gave it away. So this is an example of a solvent. A solvent is a liquid that dissolves a solute. Other liquids are available, for example, alcohol, rubbing alcohol, and also acetone as well. That's another solvent. Now, what did I actually make? So I've actually made something which combines the solute and the solvent together. It is called a solution. Okay, it's called a solution. So we've got our basic vocabulary here. The substance that dissolves is called a solute. The liquid it dissolves in is called a solvent, and the liquid formed after the solute dissolves in the solvent is called a solution. And many people actually then, when they get asked the second question after this, what's actually happening, they get really, really stuck. And the reason why is because early on in high school, you're told about solids, liquids, and gases. I've got a little model here. It's actually a gel polymer that I picked up from a local store. And this is the way in which your class teachers will be teaching you how liquid particles interact with each other. I'm just tipping it so you actually get to know the fact there's not a regular arrangement inside, but all of the liquid particles are touching together. It's very, very important to think about it, because one of the things that your teachers then ask you to do is they ask you to make that jump to think about molecules of water not necessarily like this, but like this. So what you've got to imagine is that each one of these is actually one of these, okay? So it's H2O, it's got 2 hydrogen atoms covalently bonded together to form a water molecule. It's covalently bonded with an oxygen atom there, okay? This is neutrally charged overall. However, one of the things that water actually does is it has a behavior that allows you to get from here, this solute, to this solution. Okay, and the reason why is because the particles in virtually all of the solid solutes that you meet at GCSE for sure are ionic substances. So I've got a little model here for you to consider. In terms of the structure of ionic models. Now, in GCSE, you get to know this. You get to know that there are oppositely charged ions locked in together, electrostatic attractive forces between the negative ions and the positive ions. Notice that I'm also incorporating a different word now for the particles that are actually inside a solid like this, an ionic solid, because they are ions. So what actually happens? Well, you can imagine that that the water molecule comes up to one of the ions. And say, for example, this is the negative ion. Now, water actually is asymmetrical, so it actually has a positive end, which are these hydrogens, and it also has a negative end, which is that. It's called a dipole. So what actually forms are these things called ion dipoles. Ion dipole bonds. So basically, essentially, what happens is, remember that these ends are positive, this is a negative, and what happens is this comes in and it effectively prizes out the negative. So I've got one over here. I've got this to represent the negative ion. It's supposed to be round, and you can imagine that several water molecules will actually come around and in 3 dimensions would actually surround. So this is actually favourable, because originally each of these negative ions was surrounded by a positive ion, so it's nice and stable and energetically it wants to stay in there. And if you have to try and break off the ions from your ionic lattice here, you actually have to kind of like substitute these attractive forces for something that's very new. So what actually happens is the water molecules actually allow that. So you get like a cage around an ion, forming lots and lots and lots of different water molecules. And then around that, you can imagine that this is like the first cage, and a little bit further out, you've got in the first case, you've got the negative end over here, and you've got water molecules which have positive end. So they form another cage around, and all of these water molecules suddenly coming together, forming these bonds. And this actually is really, really favourable energetically. I'm going to talk about A-levels and entropy just yet. But this is actually favourable. So it's kind of like as if they're like surrogates. So they actually look after the ion, and this ion then starts to swim around the solution itself. That basically, in a nutshell, is what happens when you actually dissolve substances. And you can imagine that if all of the water molecules are locked in to doing this, and remember that if it was the oppositely charged ion, it would actually switch around like this. Okay, so if all of the water molecules were engaged in this and were used up in these attractive forces, then you'd get to a stage where you can't actually dissolve any more solute because your water molecules can't actually substitute themselves in for the oppositely charged ion. So what you can prove this very, very easily by adding quite a bit of this solid. Just get the end bit in there. And if you try and dissolve that, you get to a stage where it gets very, very dark. Now the actual copper ions in here are blue, so it's very, very useful for us to keep track of whether we've got something that is full to capacity, so to speak, and cannot dissolve anymore. Now underneath here, you can actually see that there is still some powder here. So stirring. I keep adding, and if it does dissolve, then I will just keep adding more. If it does dissolve, it gets to a stage where you can't actually dissolve any more. Hopefully you can see that. I'll just turn this around. You can see that there's a powder right over there. So this is now what we call a saturated solution. So a saturated solution is a solution that actually contains as much solid as possible dissolved in it. Now that works at a particular temperature. And what I could do is I could actually have asked you, how do I actually dissolve that extra solute? And what you would be able to tell me is, you'd be able to tell me, well, if I heated it up, and generally speaking, if you heat things up, the particles inside, they move faster. And they would be able to store more kinetic energy inside them, and they would be able to break everything up, and they would be able to form more stronger ion dipole forces, and you talk about it like that. Solubility actually increases with temperature, and we actually just find that as a trend. So if I wanted to heat this up, I could, and I would then be able to dissolve some extra. Now, if that then disappeared, I'd be able to replace it with even more powder. Okay, so I could just keep on flushing it until I get a very hot solution which is saturated, and then what I could do is I could then cool it down, and as it cools down, the solubility suddenly drops, and that would mean to say that I'll be able to then form the crystals that you saw earlier when I showed you. And that's how we actually form these beautiful crystals. So that's called crystallization. It's a nice way of separating things out. I wanted to try and just basically have a quick introduction, mainly to remind, particularly my year 11s, of what actually happens when you dissolve things. You have a solute. Remember, the solute is the solid. Solvent is the liquid that you use to dissolve the solid. A solution is the liquid that forms. You can actually get to a stage where you add, where you don't have enough solvent to form a perfect solution. So it's saturated, and the reason why is because of these water molecules trying to bind and replace the electrostatic attractions. The forces of attraction, the electrostatic attractions that exist in the ionic lattice that you normally have when you have a solute, an ionic solid. Okay, thank you very much for watching. I hope this helps a little bit in terms of understanding and gets you into the topics that you are coming across in your GCSE. Again, bye.